Okay, so can I start? There's some signal.
Yes, sure.
Okay, good. So thank you very much for the invitation. So the title of my talk is Kerr black holes and massive higher spins. And Kerr black holes, by Kerr black holes, I mean the actual rotating, and in the universe everything is rotating, actual rotating black holes in our universe. And massive higher spins is what they are. There's some specific quantum field theories that we're going to construct. And the main message of my talk is, well, try to explain how these two things can possibly be related. So because it's an online talk, let me start from the end. Let me maybe start from some main messages and also the plan of my talk. And then I'll try to elaborate on these messages more along the way. So new era of gravitational wave physics has just come. And this leads to a challenge for developing theoretical tools for future and contemporary detectors. And quite recently, there are some old methods, so people have been solving Einstein equations since they were proposed. But recently, people from quantum field theory and amplitude community, they came into the game and proposed new techniques to address the same problem, which is effective field theory. So instead of trying to actually solve Einstein equations, what you instead trying to do is to engineer some theory that will effectively describe the dynamics of these compact objects. And this somehow leads to a question how to construct a theory with massive fields of arbitrarily high spin. Because roughly speaking, the idea is that everything from far away will look like a massive higher spin particle, so that you can use effective field theory description for that. And this leads to a very old problem, how to actually make fields with spin greater than 2 interact. So we have several recent papers, which I'll cite later, where we try to use ideas of Zinoviev massive higher spin gauge symmetry and some new approach that we developed to say something about this problem. But let me start slow, just by reminding few things that, the Einstein equations were born around 1915, and they immediately came up with several predictions that were later explicitly verified. And many other tests were performed, and in particular, we have general relativity working on our cell phones under the name of GPS. And quite recently, people finally detected gravitational waves. It was in 2016, so just 100 years later, theoretical prediction. And was also a picture of black hole taken by Event Horizon. But so the thing is that the rapid development of gravitational wave physics leads to a challenge to develop theoretical tools to solve general relativity equations for two and maybe more compact objects orbiting each other, or scattering of each other, and emitting gravitational waves. So it's quite, it is surprisingly hard to solve Einstein equations just for two compact objects orbiting each other and emitting gravitational waves. So first of all, these are nonlinear partial differential equations in 4 dimensions. So we can't think of just putting this problem on a computer because the process of collision, effective emission of gravitational waves that we can detect, it in principle can last for months and even years. So there is no way, we don't have big enough computer to solve this problem, so we should be smarter than that. So apart from numerical relativity and various approaches within this numerics, there are many old approaches, for example, post-Newtonian approximation, which is expansion in the velocity, assuming it's much smaller than the speed of light, gravitational self-force, effective one-body approach, post-Minkowskian approximation, which is expansion in the gravitational constant, and several others, which I'm not going to talk about, so I'm just giving a list to say that there are many, in fact, approaches that been with us for quite a few years. And actually, true numerics is needed only at the very last stage, where two compact objects come very close to each other and they merge together, and say two black holes, their horizons merge and they form one big black hole. Only for the last basically fraction of a second you need true numerics. The rest can in principle be addressed by theoretical tools. And what happened quite recently, just a few years ago, is that people who were previously working on quantum field theory and amplitude, say for LHC, they came into the game and proposed new techniques to solve Einstein equations via amplitudes and effective field theory. So the basic idea is that, well, we usually think about quantum field theory as something that is designed to describe particles, elementary particles maybe, so quite small objects. But the truth is that you can apply effective field theory everywhere as long as certain assumptions are satisfied. And here, if you have two compact objects, well, compact means that they're far away as compared to their distance, to their impact parameter, then essentially they look like point-like particles. And so you can imagine that you can model them just with field theory. And well, so from far away, everything should have a mass. It can have an angular momentum because everything in the universe is rotating, and it can have a charge. But there is no macroscopical charge in the universe because it's very hard to make things that are not charge neutral. So essentially, you have just two characteristics: mass and spin. And ideal objects from this point of view are black holes, because they don't have more parameters associated with them than I just said. While if you have, say, neutron stars or some alien spaceship, they can have some complicated mass distribution that will eventually affect the details of the process. But this can be, as usual, within effective field theory, this can be taken into account by turning on a bit more of operators. And so what has been proposed is that instead of solving Einstein equations, we can look for effective field theory that describes the propagation of a massive spin-s field in gravitational field. And well, one can ask why this can work at all, because in the gravitational wave, we are interested in two compact objects orbiting each other, which is a bound system, while amplitudes and QFT, they're usually interested in amplitudes and S matrix. Well, the idea goes back to classical physics. We can imagine our Kepler problem, and imagine that somebody maybe apply quantum field theory tools and work out S matrix and so on. So from this, we can read of effective Hamiltonian that describes this process. And in this Hamiltonian, there is a parameter, which is energy. And it's positive if you are interested in scattering. But as long as you have this Hamiltonian and parameter in there, you can let this parameter be negative, so that from the Hamiltonian that was obtained from unbounded problem, from the scattering problem, you can go back to the bound state problem. This is roughly speaking an idea. So you can, instead of two black holes orbiting each other, you can talk about two black holes scattering off each other. So we replace one problem by another. And we can try to use just quantum field theory tools to describe this. And here the dictionary is roughly speaking that mass is the actual mass of the particle we are talking about, and the angular momentum is a spin in Planck units. So because spin sorry, angular momentum is macroscopical, so the spin of that particle, well, is going to be very large. Well, in principle, we should be able to describe particles with arbitrarily large spin to make this work. So this leads to a question of how to construct a theory that has a massive particle with spin s interacting with gravity in such a way that the result corresponds to just solving Einstein equations for two compact objects. So that's the idea, but I would like to spend maybe a few minutes just talking about physics of spin. Namely, the message is that what I would like to explain is that the physics depends on the value of spin a lot, and this is not always appreciated because there are many communities that work just, say, on one value of spin, and they don't often talk. So in principle, what we can describe in our colliders, or whenever the concept of elementary particle can be applied, was given to us by Wigner many years ago. So combination of quantum mechanics and special relativity implies that all particles, elementary or not, they should correspond to unitary irreducible representations of Poincare group. And as such, these representations, which we also classify by Wigner in 4 dimensions, they give you several options. You don't have to observe everything in your collider. These particles don't have to be elementary. They may not be even particles. We will be talking about black holes in particular, but they should behave as such. And as far as options are concerned, we have several options. The first one is to have massless fields. So in 4D, you need to specify spin, which is integer or half integer, and physical degrees of freedom. We have 2 of them corresponding to helicity plus minus. So S, plus minus S. Massless particles are important because they're mediators of long-range forces like electromagnetism and gravity. So here, photon is spin 1 and graviton has spin 2. So there, another class are massive particles. They also have spin and carry 2s plus 1 degrees of freedom. And in principle, there are some ideas that all massive particles, they can somehow result from some sort of spontaneous symmetry breaking a la Higgs. So they may be, say, less fundamental than the massless ones. And then there are some exotic cases, which I'm not going to consider, like continuous spins and tachyons. Well, since 1939, the result was given. There are some updates. For example, if you go to higher dimensions, you have so-called mixed symmetry fields, or if you switch on cosmological constant, you can have partially massless fields. Again, this will be irrelevant. But what Wigner gave are just 3 options. So we will never see any of these hypothetical particles unless they interact with themselves, other fields, and eventually with the light that we can see. So a more interesting question, or say more fundamental question here, is which multiplets of these available options can have consistent interactions, because nature should also be described by one of these theories. And let me give a small chart, like what we know about interactions spin by spin. So first of all, well, the only fundamental particle with spin 0 is Higgs, but okay, we can consider non-fundamental particles with spin 0. So matter are spin half, and here basically you can write anything you want, but constrained by renormalizability. So then there is one line here, because starting from spin 1, you can have gauge fields, and gauge symmetry constrains interactions a lot. For example, we can take a bunch of massless spin 1 particles, like several photons, and ask if they can have consistent interactions. And the answer here, as everyone knows, is given by Yang-Mills theory. And then the parameter that determines consistent interactions are Lie groups or Lie algebras and representations thereof, which is information that was not there at the free level. This is something that comes only when you study interaction. So we can jump to graviton, which is massless spin 2, and again ask the same question. And then again, under certain conditions, you know that the solution is given by general relativity. And in particular, gravitons can't have color. And again, free graviton is just a massless spin 2 particle. But once you consider interactions, you inevitably arrive at the concept of Riemannian geometry and things like this. So if you jump back to spin 3/2, then again the result is that there are no self-interacting theories with spin 3/2. But if you extend it with a bit more of fields, in particular graviton, you can have consistent theories which are supergravities. And again, they come with a lot of beautiful mathematics. So then the next line here separates what we call higher spin and other spins. So there is something special about fields with spin greater than 2. Well, first of all, they are very complicated to introduce interactions. So there are very few theories known that somehow incorporate higher spin particles. One of them is string theory, and also what we do in the higher spin community, we study so-called higher spin gravities that have infinitely many of massless higher spin particles. String theory spectrum consists of most of massive higher spin particles and few lower spin massless states. So this is the chart, and my main message here is that somehow just small changes in spin, they lead to completely different type of mathematical structures of physics that these theories can describe. And here, the problem of higher spins, it's essentially open. There is no simple way or like exhaustive classification of theories with higher spin particles. So the problem is to a large extent open. So let me go to massive higher spins and tell you what we know in principle about them. So first of all, where you can find higher spins. So again, I'm not talking, well, exclusively talking just about elementary particles. We are not aware of any elementary particles with spin greater than 2. But so what? Effective field theory can be used for whatever particle or not even particle, as long as certain assumptions are satisfied. So, for example, we know about baryons with a spin up to 5^15/2. Okay, they are not very stable, so maybe applying effective field theory to those is not a good idea. We can also talk about nuclei. For example, there is stable isotope of tantalum that has spin 9. So you can, well, you can put it into electromagnetic field, in the gravitational field. This would be a typical example, if you want, of a higher spin particle, of a massive higher spin particle in the electromagnetic and gravitational field. So as I already said, string theory spectrum is full of higher spin fields, and in fact they're very important. They're crucial for consistency of string theory. And well, as long as you are far away from something big, it looks small, and so you can think about this as a massive higher spin particle again. For some reason, massive higher spin fields are very complicated, just theoretically. If you ask even at the free level how to write down an action and so on, it's a very complicated problem. I can explain why. So first of all, of course, a massive spin S particle should be described by a rank S tensor. Okay, this we can do. We impose a Klein-Gordon equation. That's easy. But the problem is that Lorentz covariant tensor, like this one, contains many more components than the number of physical degrees of freedom you want to describe. And in order to eliminate these unphysical degrees of freedom, we need to impose this second constraint, the transversality. And already these two formulas tell you that the theory is non-Lagrangian, because this equation can easily be obtained from a standard action. But then this additional equation, there are just many more equations we have than the number of fields. So the system is non-Lagrangian, and it takes a very tricky set of auxiliary fields that was designed by Singhagen and dating back to Firth and Pauli. There is a very intricate set of auxiliary fields that somehow allows you to write down a Lagrangian that gives equations equivalent to these ones. A much simpler approach was proposed some years ago by Zinoviev. I will be talking more about this later. Okay, so now talking about massive particles with spin. What are the success stories, so to say, to introduce interactions? First of all, if we take spin 1, massive spin 1 particles, then one can show that all interactions, they can somehow be obtained via spontaneously broken Young-Mills theory. I'm talking just about self-interactions of these. Well, for spin 3½ there is no exhaustive classification of anything, so it's the problem is open. For spin 2, again, there is no exhaustive classification of possible interacting, consistent interacting, say, classical theories that one can write, but it was quite recently that people constructed theories that go under the name massive gravity and bigravity. And again, for spin 5½ there are some recent results, but again, for 5½ and higher, we basically know almost nothing. In particular, we don't know like complete consistent theories with massive higher spin fields. But what we can do, there are several approaches on the market that one can pursue. The first one is, well, we call it Zinoviev's massive gauge symmetry. I will talk about this in a while. Then recently we proposed so-called chiral approach. And in principle, there are other techniques. For example, there's light cone gauge developed by Mitsayev, and there are some covariant approaches developed by Buchbinder and collaborators. So, but I will be mostly talking about these two. So what is the idea here? And before trying to construct some interactions of higher spin fields, let me briefly tell you what the actual relation between black holes and quantum field theory in the sense of amplitude and S matrix. So first of all, if you try to, classify possible interactions between massive particles and massless, like graviton or photon, then you'll find plenty of interactions. There is no like unique interaction there. But these people, Arkani, Hamet, and Juan, found a family among those interactions with the best, so to say, high energy behavior. And these amplitudes for these interactions, they look like this. So here you have two massive spinous particles and some massless one, like a photon or a graviton. And then, of course, we have to use this cryptic language of amplitude people. So it's not really important what these expressions are. It's important that they are available. So the amplitude for these cases have a very simple form of amplitude of a scalar field interacting with photon or graviton. This is something that we can easily imagine, times certain factors that account for massive information. They depend on the polarization and momenta of the massive fields here. So, for example, if we go to standard model and couple it to gravity so that we can also compute amplitudes with graviton, these are exactly the amplitudes you get in the standard model once S is 0, 1/2, and 1. They are written maybe in a bit unusual language, but it is standard in the amplitude community. Okay, so you have this family of cubic amplitude with the best possible high energy behavior. And it was shown by Guevara, Chirov, and Vines a few years ago that exactly these amplitudes reproduce the classical behavior of a rotating Kerr black hole whenever you set helicity to ±2, that is the graviton. So the exact dictionary is a bit complicated to present, well, within this short talk, but roughly speaking, the idea is that your macroscopical angular momentum should be expressed somehow in the units of h bar as a spin. And so when you take the classical limit, so we're interested in classical physics, so when you take the classical limit, h bar goes to 0, so therefore spin has to go to infinity in some controllable way so that your macroscopical angular momentum, denoted by A here, remains finite. This is roughly speaking the idea that spin, not surprisingly, is the same thing as the angular momentum. But because we're talking about macroscopical objects, the spin has to be very large. So in principle, we should be able to take it up to infinity. Okay, and then why I denoted this massless field by helicity H and said that it can be photon or graviton, it's because there is another construction in quantum field theory called double copy. So roughly speaking, this is a construction that, given some theory with gauge fields, that is massless spin 1 fields, given some theory with gauge fields, it allows you to quote-unquote square the amplitudes of that theory and get amplitudes of theory with graviton. So basically the slogan is that gravity is a gauge theory squared. So it's just a technique, but it's very powerful. So therefore, many questions that are complicated to answer for gravity, you can try to first answer them for electromagnetism, and then using double copy construction, you can immediately get, say, amplitude for the case where massive spin S or black hole scatters of the graviton. So therefore, we will be talking about Kerr situation and so-called square root Kerr or root Kerr. So where instead of constructing a theory with massive spin S particle interacting with graviton, we'll try to construct the same thing but interacting with photon. And this is what I will consider in mostly in the rest of the talk. Okay, so because higher spin fields have lots of indices, I won't be able to show you the formulas that we've got, but it's useful to at least show you simple example, which is a part of the standard model. So let me try to construct electromagnetic interactions of W boson. I ignore Z boson, I just don't need it for this presentation. So therefore, instead of SU2, U1, Higgs mechanism, let me take SO3 and spontaneously break the symmetry so that 1 out of 3 gauge fields remains massless, so it will play the role of the photon. And 2 other fields, they can be combined into complex vector. And here there is a relevant part of the Lagrangian that tells you how a W boson interact with electromagnetism. So we see 2 sources of interaction. First of all, there is a covariant derivative here that, of course, depends on electromagnetic field. And there is this non-minimal term where we see direct interaction between F mu, the field strength, and W boson. Well, okay, so this is a known result in the sense that we just take spontaneously broken Young-Mills and read off the part that we're interested in. But how to get this result in a way that would generalize to arbitrary spin? Because there is no such thing as Higgs mechanism for a spin-S particle, at least known now, but basically this is what we want to find. Well, the idea here, which perhaps dates back to Stuckelberg, I mean, at the free level, is to describe a massive boson as a gauge system. So we, by some trivial shift here, we introduce a scalar field so that a massive boson is described by 2 fields, the vector one and the scalar one. And the vector one has the usual massless gauge symmetry, while there is also some shift or Stuckelberg symmetry present for the scalar field. So, well, it looks here a bit like a tautology, but it allows you to count degrees of freedom quite easily because once you see the number of fields and the number of gauge symmetries, it's very easy to tell what are the degrees of freedom. While if we somehow go to the unitary gauge and eliminate this field phi, we have to prove that the theory has this transversality constraint imposed so that we have the right number of degrees of freedom. Of course, for such simple theories, everything is known, it's textbook, but I think it's a good illustration because for higher spins, it will be much more complicated to prove anything. So, okay, so let's have this free action that is just pro-K in the a-la Stuckelberg, and we try to construct interactions. Of course, the first idea would be just to covariantize derivatives, but we find that, well, by covariantizing derivatives, here we find that the gauge symmetry is lost. But we can restore this symmetry precisely if we add this non-minimal term. So the message here is that the simple recipe of covariantizing derivatives doesn't actually work apart from very, very simple cases, but for most of the cases, it doesn't work. So you need to somehow add certain non-minimal interactions. And so the best way of doing that is to use this Stuckelberg symmetry. And if we go to higher spin case, so then the idea that is thanks to Yuri Zinoviev is to describe a massive spin-S field as a sum of massless spin K particles where K run from 0 to S. Of course, it's not a direct sum. This is a wrong symbol here, but it's a direct sum as the number of degrees of freedom goes. What you actually have to do is to write down a theory that consists of the actions for all these fields with spins from 0 to S and add certain mixing terms. And in particular, the gauge symmetry has the first piece, which is the usual one present for the massless field, but there are also some mixing terms. And if you impose this gauge symmetry, you find very nicely a free action that describes a massive spin-S particle. And in particular, these sort of constraints I was talking about here, they pop up out of this action automatically. You don't have to worry about this. You can easily count the number of physical degrees of freedom. So this is what we're going to use. We want to take Zinoviev description of massive higher spin particle and push it to interactions. Well, okay, so that's good time to mention that we have 2 papers, and one of them just yesterday about this. So because higher spins have lots of indices, I won't be able to show you final results. Also, this is still an ongoing game. But basically, what we need to do is we need to write down the most general answers for all these interactions, which of course leads to lots of coefficients and tensorial structures, as well as we need to write the most general answers for gauge transformations. And then we turn the crank and try to maintain this gauge symmetry. An equivalent approach, which is sometimes easier to implement, is to use word identities for this massive higher spin gauge symmetry, which is a bit closer to amplitude. But one way or another, you have to write answers for your interactions because a priori we don't know solution, and it would be really nice to see some hidden, maybe mathematical beauty, mathematical structure that would solve the problem or all problems at once. But what we can do right now is, for example, we can write down a simple generating function for on-shell cubic vertices of two spin S fields interacting with electromagnetism. Just to give you some examples, this we already know. This is the non-minimal interaction that we need to supplement the Proca action for W boson width to have a consistent theory. Well, there's something more complicated for spin 2 and so on, but there's a closed formula for all of these interactions. In quartic analysis is, of course, much more complicated. So one thing that I forgot to mention is that there is no hope in this story for higher spins to stop interactions at a given order. For example, in Yang-Mills theory, we know that you don't have worse than a quartic interaction in your Lagrangian. But in gravity, it's not the case. If you just perturbatively expand it in metric variables, you'll find cubic, quartic, quintic interactions of arbitrary high order. This is essentially the situation we are in now with higher spins. And of course, this is due to the fact that we don't quite understand, for example, what is analog of, I don't know, Riemann tensor for higher spins or something like this, so that we don't have to hunt for these orders for these cubic, quartic, and so on vertices one by one. So the quartic analysis is more complicated, so I'm not talking about this, but it was successful. And I'm turning to another approach that we proposed recently. It's a bit strange approach. I wouldn't believe this can work, but it did. So we can go back to the original problem. So we like Lorentz covariant theories, or Lorentz covariant fields, and hence Lorentz invariant actions, for the reason that we don't want to fight for the Lorentz symmetry. So therefore, we choose our fields to be in some representations of the Lorentz group. But there are many ways, in principle, more than one way, to embed physical degrees of freedom into a Lorentz covariant field. In principle, well, if we stay in 4 dimensions so that the Lorentz algebra, well, is just SL2C, so it has 2 types of representations, fundamental, anti-fundamental. Therefore, if we're talking about irreducible spin tensors, they can carry 2 types of indices in fundamental or anti-fundamental. And as long as you take some spin tensor field like this one, with the total number of indices being 2s, you can embed your degrees of freedom into such a tensor. Then the question is how complicated equations of motion or Lagrangian are. That's a different question. And what we usually do, so in this story I just told you about, is that we try to take a symmetric tensor in the vectorial language, where these are 4-component indices. And this corresponds to a spin tensor of type SS that has 2 types of indices in the SL2C language. And then we know that this representation contains many more components than the number of degrees of freedom you want to describe. So you have some redundant component, and the whole problem, I mean, what we fight for is to make sure that these redundant components don't propagate once interactions are turned on. So we decided why not to take a representation which is completely chiral. So you have indices that live only in fundamental or anti-fundamental. This representation has exactly 2s. I should have written it here. It has exactly 2s plus 1 component, so you don't need any extra constraints, nothing to fight for. So basically, in this approach, everything you write is a consistent interaction because you don't need to make sure that some physical degrees of freedom do not propagate. But there must be a catch, and of course, a catch is that because the representations we chose is chiral, parity is very not easy to implement. So basically, everything you write in this approach is a consistent interactions, but there are very few interactions that you would be satisfied with if you want a parity preserving theory, and here we definitely want a parity preserving theory. So, and for higher spins, that was our contribution, but for lower spins, something like this was already done by Chalmers and Ziegler more than 20 years ago. For example, they chiralized, so to say, a standard model. And the way it works, I'm just giving one example so that the formulas later don't look completely crazy. Let us just take a Majorana spinner. So we have a spinner in fundamental and in anti-fundamental of SL2C, our Lorentz algebra. This is just the usual Dirac action, but for Majorana spinner. And by looking at this action, we can try to integrate out this psi with primed index. Here, we can just treat it as an auxiliary field. We can integrate it out in the path integral or just solve it equations of motion and plug solution back. As a result, what we get, so considering free theory, what we get is just Klein-Gordon operator sandwiched in between two, let's say, left-handed spinners. That's it. That's a correct action. It describes massive spin half particle. But if we turn on interactions via this nabla here, if we turn on electromagnetic and gravitational interactions, and again turn the crank, we find that there are two additional terms here, which restore the parity. So the theory by itself, if we just have covariant box operator here, doesn't preserve parity, but what restores parity are these two non-minimal interactions that we need to add. But in any case, we have to add some non-minimal interactions also in the game with massive higher spin symmetry. So it's always about adding some non-minimal interaction terms here. So by the way, FAB here is just the self-dual part of the Maxwell tensor of this external electromagnetic field that we couple everything to, and R is the scalar curvature. And you can try to do the same thing for all other spins. So that's an approach. And what we're looking for, and okay, I'm closing to the end of I'm close to the end of my talk. So what we want to construct is a black hole Lagrangian, namely an effective Lagrangian for a massive spin S particle, so that once you compute amplitudes out of this Lagrangian, you get exactly what you've got by solving Einstein equations for black holes. And why I'm talking about black holes is because there are some theoretical signs of simplicity of this theory. So basically, what we want to look for is the simplest possible theory that makes massive spin S interact with electromagnetism or gravity. We believe that this theory will describe dynamics of black holes, while turning on some non-minimal components in that theory will correspond to various corrections for neutron stars and or other less symmetric, so to say, objects in the universe. So, okay, so we have this free action, and we're looking for some non-minimal interactions so that everything is fine. So, but the first step, of course, is to introduce minimal interactions, which are hidden in this box operator here. And we can ask how bad this action, even without adding non-minimal terms. Well, it's not that bad, because first of all, it reproduces half of the amplitudes that we want, the amplitudes of black holes. Another half, no, but we will see how to correct this by adding non-minimal interactions. But there is something remarkable about already this simple action. I just abbreviated indices here. There is something remarkable about this action because it already reproduces infinitely many of amplitudes that were obtained from unitarity methods. So again, these are some nice minimal amplitudes, so they are supposed to belong to black holes. And this action reproduces infinitely many of these amplitudes, where you have all helicity plus gravitons or photons. But whenever we go to mixed or helicity minus sector, it's not that bright. So for example, this amplitude is not reproduced automatically. You need to add some non-minimal interaction, which is presented here. Okay, I'm not writing down the indices, but it's still a one-line expression, even if you write down the indices. So this restores a parity at the cubic level, pretty much like adding these non-minimal terms here restores consistency at the cubic level within Zinoviev formulation. Okay. Tick. So again, coming back and summarizing, the quartic problem is very complicated just because there are lots of terms that you can write. Also, it's very typical for this sort of perturbative expansions that once you at some order n, say quartic order, you have plenty of free coefficients that you can't fix unless you go to the next order. And this is exactly the situation here, because it's already technically challenging to do something at the quartic order. So we can't go to the quintic or sextic to fix some coefficients at the quartic. So we use some additional assumptions here. The basic ones like parity, unitarity, of course, massive higher spin symmetry, and also consistency with some already known lower order terms. And this way we got quartic so-called Compton amplitude describing interaction between two massive spins and two photons or two gravitons. And inverting this statement, so up to the quartic order, we have a theory that describes consistent interactions of massive spin S with photon or graviton. Okay, so let me summarize. So gravitational physics gives us new window to the secrets of the universe, and there are some detectors that are running now and many more, well, some more are coming that will allow us to detect many new processes and also over the wider range of parameters. So therefore, precision calculations in demand. And if we try to use effective field theory approach, then it all boils down to finding a theory that makes massive spin S field interact with gravity or photon. And this is what we're looking for. And with the help of massive high spin symmetry and also chiral approach, we were able to find such theory up to the quartic order. And of course, complete theory of black holes is yet to be constructed, but well, it should look like a string theory a little bit, provided you you include interactions that can change mass of these particles and spins. So you include particles with different spins and different masses into a single theory. So essentially you'll have a spectrum that is pretty much reminiscent of string theory. So we will see if this theory makes more sense than just effective theory. So thank you very much. I stop here. I think I'm on time, hopefully.
Okay, thank you very much for your beautiful talk. And I am glad to let the microphone to questions. Who wants?
Well,
maybe we can try to start discussion and do not limit ourselves.
may I ask a couple of questions on this talk?
Yes, of course.
As for me, you are welcome.
Yes. Well, first of all, very interesting talk. Thank you. If I understood what you said at the beginning, we don't really know how to solve for two compact stars in GR, but we can get reliable results for the gravitational radiation emitted by a binary pulsar, provided they don't get too close. I think that's what your claim was. So
yes.
The question is, how close can they be before we have to do something extra? Because the orbit is decaying, so eventually it will get there.
Well, if you mean in terms of actual parameters, that's very complicated to answer. But I think the idea here is that even that thing, the Taylor pulsar, you can model with just quantum field theory techniques, but that would be just one diagram contribution. So you add it, it's almost a textbook, so that would work. But there is the problem is that the range of objects that you can in principle observe in the universe is very wide in terms of eccentricity of the orbit, ratio of mass, like relative velocity and so on. So there is a big room in this space where you can use quantum field theory without any doubts, just as an effective field theory. And basically, you can't use it only very close to the merger, which is, I think, usually it's like the fractions of seconds, where they actually. So for this, you can't use quantum field theory. Or everywhere else, well, almost everywhere else you can. And this direction has just started recently, while many of the old methods that I listed on one of the few slides, they were available for decades. And immediately these QFT/amplitude techniques, they gave many more orders in post-Minkowskian and post-Newtonian expansions that people managed to compute over the last 5 decades. So you just need like a couple of years to do everything that people accumulated so far. And I'm not saying that the other techniques, they don't have their own advantages, but there is certainly something that quantum field theory takes into account much more efficiently.
Okay. I also have a general question. This whole use of quantum field theory and amplitudes is in the end going to give you an expression that depends on h bar. And you discussed a case where you could get h bar to go to 0 by taking this infinite limit. But let's suppose we don't do that. What is it that, how is it that you can have something which is h bar dependent and have it still describe a classical black hole?
Okay, sorry, I wasn't clear about that. So actually what's happening is that you take your honest quantum field theory calculation and you actually send h bar to 0, but you also keep certain things fixed. For example, at a spin times h bar, you want to keep it fixed, very large, well, because it's macroscopical, but fixed. So you do actually send h bar to 0. So in the final formulas, there is no trace of h bar.
Oh, I see. Okay, so what you were actually doing was taking the limit h bar goes to 0 in the end. It's not the quantum field theory. It's this very technical h bar goes to 0 limit that you've constructed.
Well, so but I should warn you in the following way that taking h bar to 0 is not the same thing as keeping all 3 level diagrams. So if you carefully track down where h bar occurs, you have to compute quite loop diagrams as well. So what I'm talking about is not solving classical equations for some other theory and taking 3 level. That would be naive h bar to 0. But here there are certain quantities that also scale with h bar. So taking h bar will keep lots of loop diagrams, and that's actually the technical challenge, so to say, to extract those. But amplitude community, they are in possession of lots of very efficient techniques to do that.
Okay, thank you.
Thank you.
What else?
My question again to Dr. Skvortsov. Prior to the question, I'd like to know that the gravitational waves, which were mentioned in the beginning of your talk, were invented not by Einstein in 1916, but by Poincaré in 1905, with the prediction that the velocity of propagation is equal to the velocity of light. Now, to the question is there any limitation for the spin at a given mass, or it is maybe arbitrary?
Okay, thank you very much. So yeah, about history, I mean, I can't disagree with you. There's I think there is a saying that for every result there is kind of predecessor. So maybe even before Poincaré, somebody was saying something like this. But my point was kind of that it took at least 100 years between the theoretical prediction and the experimental confirmation. Okay, now coming back to your question. So because we send h bar to 0 and the macroscopical angular momentum is, roughly speaking, spin times h bar, you have to take s spin to infinity to extract the classical limit till the end. So that's why we are interested in theories where spin is a free parameter. There are no, as far as I know, there are no theoretical limitations intake and spin to be very large. In fact, there are these theories, for example, string theory or higher spin theories, where where multiplets of fields contain multiple of physical states. They contain states with arbitrarily large spin, so it never stops. There is no like upper bound to the spin, and this still works. So here we also need a theory where spin can be arbitrarily free parameter. So it should not be small because it's not interesting for the limit, but it should be arbitrarily large in principle.
Okay, thank you. I see. Thank you very much. I understand.
If I could just add one very small comment. The infinite component Majorana representation of the Lorentz group does go up to infinite spin because it's an infinite tower. And it's a completely well-defined theory. It has some problems, but at least you can write it down very straightforwardly.
Yeah, I totally agree with you, and the examples I gave in the same line. But I think Majorana is just a free equation that describes infinite spectrum. So the problem usually pops up when you try to construct some interactions, and this is what's definitely happening with higher spins, because just naive recipe of covariant Ising derivative as to have electromagnetic and gravitational interaction leads to an inconsistency immediately. So, and then we use this Zinoviev massive gauge symmetry or some other approaches to deal with that. So the problem usually comes from interactions. But as far as I know, like coming back to the previous question, there is no upper limit to spin in principle. And there are examples where it's unbounded.
I have probably a related question. For quantum spin, there are bounds coming from density matrix positivity. Is it possible that something survives in the H bar going to zero limit?
Could you please maybe elaborate a bit more? I don't.
Well, just there are if you consider spin and there is a spin density matrix, its eigenvalues are positive, and it puts the constraints on the scattering amplitudes. They are practical and they are used. So, is it possible that something will put some constraints in the limit S to infinity H bar to zero?
Okay, so sorry if I misunderstood the question. The way I understood it is the following, that so in fact, if we're talking about unitarity, for example, tree-level unitarity, then usually, well, the higher the spin, the worse contribution is. So these contributions diverge, in fact, at high energies, and they diverge more the higher the spin you have. And this sort of divergences are cured, say, by string theory, because it has exactly because it has states of unbounded spin, so that you need to sum certain series instead of considering every Taylor coefficient individually, and then the result is convergent. So here we are not worried about that, because we are within effective field theory approach. So we are not thinking about these theories as being fundamental, where, for example, you can actually take high energy limit. Our limit, the classical limit, is right the opposite. You take your energy very, very small, transverse momenta very, very small, okay, and then these sort of problems, they don't show up.
Well, actually, density matrix positivity is indeed a counterpart of unitarity. So in a sense, that all eigenvalues of density matrix describing the particle with spin are positive. I suspect that maybe in this classical limit, this can be trivially satisfied. So just maybe because they do depend on spin, but maybe still something non-trivial can survive. I don't know.
Yeah, so we definitely see something surviving to the quadrichord, and I think this is like the general question about applicability of effective field theory. So as long as your energies are not very high, it is applicable. And because you actually see these processes happening in nature, there must be some theoretical way to describe them.
Okay, thanks.
Thank you.
Yes, Professor Shapiro, would you like to say something?
Yeah, I have the question which I typically ask people who do similar things. So at the beginning, you show some Feynman diagrams for black holes, and you know, if I understand correctly, you put some on these diagrams internal lines of black hole. So the question is, this means you quantize black hole as a free particle or free field, better say.
No. So what we do is we replace black hole by particles, and we manufacture interactions of these particles where these particles don't you don't create pairs, anti-pairs, particles, antiparticles from vacuum or anything like this in this limit. So we just manufacture a theory of a particle where if you compute the scattering, you get exactly the same scattering if it was two black holes passing around each other and going to infinity. So they don't merge in this process. There are no actual quantum effects, like, okay, we don't quantize black holes. It's just a theory that produces exactly the same results as a completely classical system.
So but you have loops, and there are internal lines of these objects in the loop. It means that this object is quantized for me, at least.
Well, the thing is that it's not, because if you carefully consider h bar going to zero limit, then you don't have integration over these offshore virtual states and so on. So there is no actual quantization going on. You do have loop diagrams, but you need only, so to say, small piece of these loop diagrams. You are not computing loop diagrams. In particular, non-renormalizability of gravity plays no role here, because you will never find a closed loop of gravity on these diagrams as well.
No, non-renormalizability is not the point. The point is that I don't like to quantize macroscopic objects, including black holes. And
yes,
I think it is not a correct thing. But if you put propagator of this into the diagram, internal lines of the diagram, then we know that Feynman diagrams can be generated from the path integral, and internal lines correspond to the field, which is a integration variable in the path integral. So
yes,
you basically, I'm not completely convinced, let's say, but maybe you will understand better. Okay.
Yeah, so the thing is that we are not computing the full path integral. As I said, this h bar going to zero limit is a bit subtle in the sense that it keeps a bit more than you would naively assume, like tree level. It keeps some parts of loop diagrams as well, but still this is a very small piece of the full path integral. But it's just about taking a classical limit. I think in principle, what many people do in practice, they actually compute something and they take classical limit, but there are also techniques how to take classical limit in loops immediately so that you don't have to compute any loop. So, but the subtlety is in taking the classical limit. There is no actual quantization going on.
Okay.
Thank you.
Let me remind that we have heard 5 talks in this evening session, and we can discuss all of them now. You remember we discussed very wide range of problems. For example, gravitational effects and the compatibility with general relativity, such things as black holes, as cosmology, as gravitational waves. And from the other side, we discussed quantum field theory, and we hope it can be applied to this problem, to these problems. So it is a great range of topics in this discussion, and we are happy. We were happy to hear all these beautiful talks. And now what we would like to organize is some cross-examination. Maybe you can attack yourself or attack your colleagues with different and strong questions. And you feel free, as you will, if you have a glass of wine or shot of whiskey, and can you try?
Can I ask a question, which I had a question addressed to other speakers, but they are absent now. Can I ask my question to the community?
if it is not absolute and not for the whole night, you can.
No, that's a short question. Are there any observational proofs concerning the dragging of regular matter by dark matter?
We discussed dark matter in the morning session, and I'm afraid that most experts are outside now. But anybody could answer, could try. Are there any who wants to answer this question? Nobody. So I see it is a too difficult question.
Thank you. So no experts now here.
Probably yes.
Maybe I can try to answer the question. The general way that dark matter is considered, it provides an external potential for luminous matter to fall into. And most of the cases are just looking at the static consequences of doing that. Whether or not, I mean, the question you're asking, which is something I've always puzzled over, is if there is a lot of dark matter in the Milky Way, there's going to be dark matter in the solar system. So what does that do to objects in the solar system? Does it in any way modify the motion? Perhaps the most sensitive place might be what would happen to a binary pulsar if it's two compact sources going around each other in a background which is dark matter. So there must be some kind of a friction. I think that's what the question is. And I think it's, as far as I know, it's not, it's regarded as too small to be relevant, but I'm really not an expert in the field.
I am talking about the gravitational dragging, not friction, but gravitational dragging. So we have heard the talk by Professor Kazima Bambi, who discussed accretion disks, and assume that in accretion disks there are some dark matter particles, and there are some considerations that says that dark matter particles can move around the black hole faster than regular particles, and in this case these dark matter particles can drag regular matter particles, making them move faster. And can these effects be visible?
It seems to me this is a question to Professor Cosimo Bambi. Is he?
Yes, he's absent. He's absent now.
Then you can send him email.
Is there his? Well, okay, I will find his address in internet. Okay, good. Thank you.
What about Mikhail Volkov? Is he here? No. So Alexander Zakharov also disappeared. So who we can examine? What about Ilya Shapira? What if I ask you about some simple question? What effects your model can calculate? Can you calculate corrections to black hole metric or something else? Илья тоже absent?
So this is Petrov speaking. I have a very stupid question, but nonetheless, if somebody can say concerning the formation, the process of formation of a black hole. For example, if I ask how this process proceeds and how much time it takes from the very beginning of something to the end where the black hole is already formed. Is there any some kind of idea about the scale of time for that process? This is a question to those who can reply.
Well, I can say, well, so related to my talk, which was the last one, that, okay, it's not happening yet, but in a few years we'll have more detectors. And the idea is that you should be able to detect signals that are months and years long. So, of course, I mean, they start to emerge maybe billion years ago, but the detectable part can last for months and years.
Mhm.
Is the time of formation, according to you, is infinite? Till you will receive the last signal from black hole, I don't know what.
No, it's not infinite. Just, I mean, there is some time where gravitational waves are very, very weak, so we don't detect them. But then there is this stage where we start to detecting them, and it can be very long, like months and years in principle. This should be possible to detect mergers like that, and then they merge, and then you detect the last splash of gravitational waves, and it's gone.
And related, I don't think that we have now somebody who can reply to my question, because this concerns the practical astrophysicists. But nonetheless, if there is some observations which can say, show the process of formation of the black hole in the universe or not, maybe somebody has seen something like that.
Well, probably Cosimo Bambi would be able to answer, but I can answer to the question which was directed to me. And I believe that the answer to this about formation and observation would be negative. But I'm not sure.
Ilya, I have asked you when you were out.
Yeah, I started to answer. Then I noted that the microphone is switched off. So, yeah, I think there was one paper of this sort, and one my former student is now trying to make it different. But unfortunately, I don't remember the exact reference. I can check it. Okay, but in principle, it would be interesting. You mean taking these quantum corrections induced by anomaly as a small corrections and trying to find small corrections to the black hole solution? Yeah, it is a reasonable question. Yeah, we're trying to do it now.
Yes, thank you.
Because the self-consistent solution would be to consider quantum correction to consider a Hawking radiation, or let's say vacuum state for the black hole, and simultaneously make correction to the solution and make it like self-consistent. But this nobody could ever do. And I'm not expert in black holes, so I have to rely on some real specialists, let's say.
Yes, but I mean the dream to unite quantum field theory and general relativity, and you are on this way to realize this dream.
No, I think the problem to make unification of particle physics and gravity, the main problem is with experiments, because we don't have experiments, not with theory, because we have many theories. But since we don't have any experiment, so it's difficult to work with poor theory. Okay, so it's my personal opinion. So I think the main problem is there is no visible possibility to check anything.
So you hope that in our lifetime we will see some result of quantum gravity experiment?
No, I don't think so.
Yeah.
Sorry,
Can
who is speaking? Who was asking me? Could you please tell your name?
Vladimir Solovyov.
Ah, yeah, I realized it you by voice. Nice to see you. Okay.
Can I make a comment on the question of quantum gravity?
Yes.
Well, I'll actually talk about this on my own talk on Thursday, about how it's possible to construct unitary renormalizable theories of quantum gravity. Ilya is right that we radiative graviton loops we can't monitor at the moment, but we do have an indirect piece of information, and that is that when we do gravitational experiments, we get finite answers. And yet, if we just take Einstein gravity as is and do radiative corrections, the radiative corrections are going to be infinite. And so we have sort of negative, we have negative measurement, namely we're not measuring something infinite, whereas the theory is suggesting that it should be. And so I think we need to think about, well, how do we get rid of those infinities? And what do we finish up with? I think Ilya is sort of saying, well, eventually we'll come up with a full theory. Then we'll be able to have finite radiative corrections, but it's too early to be able to test them. And I think that's certainly correct. But on the other hand, it's in the meantime they're infinite, and they have been tested, and we've seen that the answers are not infinite, that the measurements we make are finite. So there really is a challenge there.
Thank you. So
I'd like to address, first of all, to Evgeny Skvortsov, but to other people also. Didn't you think about, when you consider the relationship between spin and mass, did you think about radio trajectories?
Well, we do, but maybe indirectly. So this is related to what I said on the last slide, that in principle, if you try to model like black holes or something else in general relativity, well, because of gravitational emission, this body can lose its mass, it can change its spin and so on. So we consider for now what's called conservative approximation, when none of these things is happening. But if you want a complete theory that describes these processes, you might think of a theory that has particles of all spins and all masses, maybe with some gaps or even continuous, that would incorporate all possible interactions capturing these dynamics. And this theory can look essentially like string theory, well, in particular in the sense of having trajectories.
To this end, let me remind some curious fact. Some 30, maybe 40 years ago, one theoretician from Dubna, Muradyan, he constructed the plan, the graphic of the dependence of the angular momentum of galaxies against their masses. And he obtained the curve, which reminded very much radio trajectory observed in the hadronic physics. This was published, maybe it was just a Dubna preprint, but it was very interesting. Okay.
So I would like to thank again all the speakers of today, and we are pleased to hear such beautiful talks, and of course we should think about them more than now. And sorry, I hope you will participate in our workshop other days also, at least at some talks which may be of interest for you. Thank you again, and goodbye. Goodbye.